We are at the 11:45 mark and we are eager to get started with the session. It is so lovely to see so many of you here. Unfortunately, one person who is not here, who was supposed to be here, is the convener of the session. But as Jeff Reeves and I are doing this together, I will do the honors now of, first of all, congratulating Dr. James Klimchuk with being this year's winner of the Parker Lecture Award for our section. We're extremely happy to present Jim with this award. And I'm sure he's happy to present us with a lecture in that honor. But to introduce Dr. Klimchuk properly, better than I could do, it's my honor first to introduce to you Dr. Holly Gilbert, who is the director of the High Altitude Observatory from NCAR, as she will give a proper introduction to Jim. So, Holly, please.
No need to clap for me. I'm going to move this down. Jim, you'll probably have to move this back up. I'm height challenged. Well, welcome everyone. I'm delighted to be here and to introduce Jim Klimchuk. He doesn't really need much of an introduction, I don't think, but I will highlight a few things about Jim. First of all, he got his PhD in astrophysics from the University of Colorado in 1985, and I'm from Colorado, so we have that connection. I wanted to highlight some things about Jim that many of you know already, but he really has made absolutely fundamental contributions to a wide variety of solar physics topics. The breadth of his impact is unusual, but what makes him unique in the field is his in-depth use of all theory modeling and observations. He's made pioneering contributions to not only observational science, but also to basic theory. I think he is driven by a passion to see science done correctly. I think anybody that knows him knows that that's true. He's won multiple awards, including many NASA awards. He's an honorary fellow of the Royal Astronomical Society. He won the John Lindsay Memorial Award for Space Science. He also has served in multiple leadership positions and service positions. He was the AAS SPD chair, SPA president. He also served in the IAU as a president of Commission 10 on solar activity. He's currently serving on NASA HPAC. So he just is an incredible service member of our community, and I really appreciate that, and I think we all do. But not only is Jim a world-class scientist, he is as authentic a person as you'll ever meet. He's incredibly kind and caring, which makes him also a very excellent mentor. And it's very difficult to quantify the positive impact he's had on our community. Lastly, but not least, he is really a truly wonderful friend, and I am lucky to call him my friend. And so on that personal note, I will turn it over to Dr. Klimchuk, and congratulations, Jim.
Well, thank you so much, Holly, for those overly generous words. I think maybe you're feeling guilty about all the teasing through the years. And thank you, Teresa, as well. This is really a great honor for me because Gene Parker has been a hero of mine for essentially my entire career. It's absolutely staggering how much he's done for our field. He's made seminal contributions in so many areas. I mean, nowadays we think of him for his work on the solar wind because of Parker Solar Probe, but he's made major important progress on problems like reconnection, we know about that, thermal instability, solar dynamo, many other topics. But the work of his that's had the biggest influence on my career is his work on coronal heating. As I'm sure you know, the corona is some 3 orders of magnitude hotter than the solar surface. Understanding why that is the famous coronal heating problem. Now, Gene suggested back in the early 80s that the corona is heated by small bursts of energy related to magnetic reconnection. And he estimated the energy in those events as being about 1/100000th that of a full-size flare. So he coined the term nanoflare. And that basic picture has guided our thinking for the last 4 decades. And I just realized I don't have, you're looking at this ugly guy up on the stage. I should have brought up my presentation. All right. There, that looks a bit better. Okay, so this is the topic of my talk, coronal heating. And I need to make the very important distinction between the magnetically open and magnetically closed corona. In the open corona, only one end of a field line is rooted to the solar surface. So this includes coronal holes and the solar wind. And it's widely agreed that those areas are heated primarily by waves. But in the closed corona, both ends of a field line are rooted to the surface. So this includes active regions, which are the very bright features in the image here, which contribute the majority of the solar spectral irradiance, at least at short wavelengths, and also quiet regions. And it's generally agreed, though not universally accepted, that active regions are heated primarily by reconnection, with waves playing a significantly lesser role. As for the quiet sun, we really don't know at this point whether it's waves or reconnection that dominates. All right, so I'll be talking today mostly about active regions and mostly about reconnection-based heating. But I would point out that in the coronal environment, wave heating is also very impulsive in nature. So much of what I'll be discussing, in fact, applies to waves as well. Now you're going to notice a couple of themes running through my talk. First of all, this problem involves an enormous range of spatial scales. Secondly, there are very important couplings between these scales and between different parts of the atmosphere. I'll also try to point out some commonalities with the geospace system. But before diving in, let me take this opportunity to thank the many wonderful collaborators I've had through the years. Far too many to list. Any successes I may have had are due in large part to these people. So I want to thank them not only for their collaboration, but also for their friendship. So Holly, that really hit home with me what you said. I've been so fortunate to have had so many great friends in my career. So thank you so much. All right, so let's take a look at a fun movie. This movie was made by the Atmospheric Imaging Assembly on the Solar Dynamics Observatory in the 171 angstrom channel. So this shows plasma at about 1 million degrees. And in looking at this, you might say, well, yeah, of course, coronal heating is highly impulsive. I mean, look at all this rapid variability. Well, the movie is misleading. It takes 27 days for the sun to execute one rotation, so time is greatly sped up. And the fact of the matter is that with present day instrumentation, we are not able to detect individual nanoflare events. We're always looking at them in aggregate. And so we infer their properties and their existence based on the collective emission that they produce. And we have some pretty nifty techniques for doing that. I mean, we have, I think, convinced ourselves quite convincingly that they do in fact exist, even though we do not see individual events. And we've even been able to sort out some of their more general characteristics. All right, so what are these nanoflares? Well, to help you understand that, I need to go over some basic principles. Is this a little too close here? A little echo? Does it sound good to you guys out there? Okay, great. So here are the basic principles. First of all, the plasma beta, the ratio of the gas pressure to magnetic pressure, is very small in the corona, but is very large in the photosphere. Therefore, the magnetic field dominates the plasma in the corona, but the plasma dominates the field in the photosphere. Field-aligned thermal conduction is very important. So we have both energy and plasma flowing easily along magnetic field lines, but not across them. And therefore, temperature and density tend to be fairly uniform along the field, but not necessarily across it. So plasma structures trace out magnetic field lines. Now, it's not the case that we only have magnetic field where you see these beautiful bright coronal loops. There's field everywhere in the corona because the beta is small. The field is space filling. It's just that particular subsets of field lines are lit up by stronger coronal heating. All right, so those are the basics. So what about this coronal heating and these nanoflares? Well, that story begins in the photosphere, where photospheric convection is occurring. And this is the engine of coronal heating. This beautiful movie here was made by the Daniel K. Inouye Solar Telescope, or DKIST. Came online a couple years ago. These are some of the very first observations, in fact. And these show how incredibly dynamic the photosphere is. It's constantly churning. Hot plasma is rising buoyantly up from below the surface, reaching the surface, spreading out, cooling off, and sinking back down, giving rise to convection cells. And the pattern of convection cells, as you can see here, is constantly changing. Now, this movie lasts only 10 minutes of solar time. So there's a lot of evolution just in those 10 minutes. Now, the coronal magnetic field is rooted in this churning plasma. So you can well imagine that the foot points of the coronal field lines are being displaced about the solar surface in random and chaotic ways. The second thing that you can notice from these observations is just how non-uniform the magnetic field is in the photosphere. The magnetic field is contained in intense magnetic elements that we call kilogauss flux tubes. And the bright features you see here scattered throughout the intergranular lanes, these are where these kilogauss flux tubes poke up through the photosphere and extend up into the corona. So the corona is highly structured. You can see that in this beautiful image here. This image was made by the High-C rocket experiment. It's the highest resolution coronal image ever made. There's plenty of fine scale structuring. But the structuring, we believe, extends to, in fact, much smaller scales. There are elemental magnetic strands associated with the kilogauss flux tubes, and we estimate that there are about 100,000 of them in a single active region. And even these features here, can you see, is my cursor there? You don't see my cursor, do you? Is there any way to get the cursor to show up on the screen? Hello?
Yes, sir.
Can I get the cursor to show up on the screen at all?
It should be there. Hang on.
I don't want to do that. No, I see it on the screen here. It's a nice big red arrow, but it doesn't show up on what you see.
I can try and change the contrast if that'll help.
Nah, that's okay. Never mind. Thanks. Let's go on. Thanks.
I can call for a laser pointer if that would help.
Probably not. So thanks anyways. Okay, you'll have to remember that I can't point to things. Anyways, I was going to point out that you have these monolithic looking things, these bright loops, but they're not monolithic at all. In fact, they are multi-stranded. All right. So these strands are rooted in the photosphere. All these crazy motions down there are causing the strands to become tangled and twisted up in the corona. And these strands are in contact with each other in the corona. That's not true in the photosphere. The field is really highly concentrated in the photosphere, and the kilogauss flux tubes are widely separated. But as the field extends upward into the corona, it goes into a low beta region, and it rapidly flares out to become space filling. So these magnetic strands in the corona are touching each other. And because of all the tangling and twisting, there's an abrupt rotation of the magnetic field direction across the boundary between two adjacent strands. Therefore, we have a current sheet by Ampere's law. Okay, so we have all this stressing going on by the photospheric driving. It's building up in the corona. Eventually, the coronal field breaks locally. These current sheets go unstable and reconnect, and that is the nanoflare. All right. So here's the first example of coupling that I talked about, coupling between the photosphere and the corona.
People online won't be able to see where you're pointing.
Right. Okay, thanks, Jeff. So for folks online, I might use this laser pointer. I'll try to avoid it. Except it doesn't work. It's okay, Jeff. That's all right. Yeah, okay. All right, so coupling. The driving happens in the photosphere, but the actual energy release that heats the plasma, that happens high above in the corona. Also an example of the extreme disparity in spatial scales. Active regions are about 100,000 kilometers across, whereas these current sheets, at the time they reconnect, are much thinner, about 1/10 of a kilometer. So a 6 order of magnitude difference in spatial scale. Now, as thin as these current sheets are, they are in fact rather thick by some measures. For example, this thickness is quite a bit thicker than the classical Sweet-Parker current sheet thickness. Now, reconnection begins with the tearing instability. And as a current sheet is thinning down toward the Sweet-Parker scale, it goes unstable long before reaching that scale. So we do not expect Sweet-Parker current sheets in the corona. This was pointed out previously by Fulvio Pucci and Marco Velli and Anna Tenerani. Also, this 1/10 of a kilometer thickness is very large compared to kinetic scales. The kinetic scales in the corona are about 1 meter. This means that we can study the onset of reconnection and early development using resistive MHD. There's no need for a full kinetic treatment as there is in the magnetosphere. But of course, small spatial scales do develop as the reconnection proceeds, and then kinetic effects are important, even in the corona. All right, so when a nanoflare goes off, how does the plasma respond? Well, let's first consider the case of steady heating, and we have an equilibrium loop strand. Now, to achieve energy balance all along the strand, the atmosphere sets up the structure shown on the left. This is temperature, pressure, and density as a function of position along the strand. You're going from one foot point up over the apex to the other foot point. And as you can see, temperature, pressure, and density are quite uniform over most of the strand, as I pointed out earlier. However, there is a thin layer at the base of the loop where the gradients are extremely steep. This is called the transition region. But the diagram on the right indicates the energy balance in this equilibrium loop strand. Energy is put into the corona by coronal heating. Roughly 1/3 of it is radiated to space from the corona. The remaining 2/3 is thermally conducted down the leg to the foot point and radiated to space from the transition region. Now you may think it odd that this very small volume transition region emits twice as much radiation as the much larger volume corona. That's because the plasma of the transition region is a very efficient radiator. The emission varies as density squared, and the transition region is much denser than the corona. Another example of coupling between the corona and transition region this time, a very, very important energetic coupling. And an example of the disparate spatial scales. The temperature scaling from the corona is roughly 100,000 kilometers, but in the lower transition region, it's only 1 kilometer. So once again, a many order of magnitude difference. All right, so that was steady heating. How about impulsive heating, nanoflare heating, where the loop strand is inherently dynamic? Now the energy balance looks much different on the right here. We have a huge amount of energy being dumped into the corona all of a sudden. The corona can't even come close to radiating away that energy, even a small part of it. So the vast majority of it gets thermally conducted down to the foot points. Or even the transition region, with all of its efficiency at radiating, can't handle that huge influx of energy. So the plasma heats up and it rises rapidly, expands rapidly up into the corona. And that process is called chromospheric evaporation. There's an energy associated with that upflow. It's usually mostly enthalpy, but the flows can become quite large and they can approach sonic or even supersonic at times, in which case, of course, kinetic energy is also important. Now, the plot on the left shows the evolution of temperature and density. These are the average temperature and density in the strand. You see the nanoflare goes off at the time t equals 0 there. Temperature rises abruptly, in this case to over 10 million degrees. There's the very intense thermal conduction flux, which is driving the evaporation. So the density is rising in the strand. But this very same thermal conduction flux that's driving the evaporation is also cooling the coronal plasma. So the coronal plasma's temperature is going down, very precipitously, at least at first. Well, the thermal conduction, it slows down, it diminishes, the evaporation slows down, eventually it stops. And the strand then goes through a slower period of cooling and draining. And all that material that had been evaporated up into the strand slowly collects back down on the foot points. All right, the same kind of thing happens in the geospace system, ionospheric upflows. We have energy coming down from the magnetosphere, being dumped into the ionosphere, causing the ionosphere to flow upward. This beautiful diagram is from Bob Strangeway and his colleagues. Shows all the many important processes taking place. Let's just concentrate on the right-hand side, if you would. So the blue represents the downflow of energy from the magnetosphere. There are two sources. We have electron precipitation, or energetic electrons. We also have that in the sun. Solar flares in particular produce huge amounts of energetic electrons. It's a major part of the energy release. With nanoflares, we're not so sure. We can rule out large numbers of highly energetic electrons in nanoflares, but there could be copious amounts of mildly non-thermal particles. We just don't know at this stage. Also in the magnetosphere, we have thermal conduction as a source of energy to the ionosphere. That wasn't part of this original chart. I added this after discussions with Alex Glasser, who tells me that thermal conduction is a very important source of energy into the ionosphere from the magnetosphere. So as energy goes down, heats up the ionosphere, it flows upward, and this upflow is potentially very, very significant. I mean, some people believe that a significant amount, if not a majority, of the magnetospheric plasma comes from these ionospheric upflows, not from the solar wind. So a very important process, completely analogous to chromospheric evaporation. An important property of nanoflares is their frequency. The example I showed earlier is one extreme example where we have a long delay between one nanoflare and the next. This is low frequency heating. On the right, I show a different situation, the opposite extreme, where there's only a very short delay between successive nanoflares. This is high frequency heating. And I would point out that these two cases have the very same time averaged energy input. It's just that the nanoflares on the right are 10 times less energetic and 10 times more frequent than the ones on the left. And you see that the consequences for the thermal distribution of the plasma are really very extreme. On the left, we have wide swings in temperature and density. On the right, we have density and temperature fluctuating about roughly constant values. This will clearly have a big impact on the spectrum of emitted radiation. You know, the ratios of hot to cool spectral lines will be much different in these two cases. And that has important space weather consequences, because where in the Earth's atmosphere the radiation is absorbed depends upon the wavelength of that radiation. So if we really want to make significant advances in predicting the solar spectral irradiance, or even nowcasting it well, we have to understand coronal heating. All right, so here are two extremes. Of course, we can have nanoflares at intermediate frequencies, and we've inferred from observations that that is in fact the case. An active region has a whole distribution of nanoflare frequencies from low to high and everything in between. So let's take a look at a single strand that's heated by a distribution of different nanoflare energies and frequencies. This is temperature as a function of time. Now, the nanoflares in this model here came from a simple cellular automaton model that describes or accounts for the tangling of the magnetic field by the photospheric driving. And it assumes that two adjacent strands reconnect and release energy when the misalignment angle between them reaches a critical value. So we end up with a wide distribution of energies and frequencies. You can see that here. At sort of the middle times, the frequency of nanoflares is fairly high, so the fluctuations are relatively small. At other times, there are big drops and big jumps in temperature when the frequency of heating is low. So let's imagine observing this strand with an instrument that's sensitive to about 8 million degrees, maybe a sensitivity spanning between 7 and 9 million. It's indicated by this bar here. What would we see? Well, we would see this strand brighten and fade at particular times. You know, at times when the light curve here crosses the yellow band, we would see a brightening. But much of the time, the strand would be faint. Now, if we could observe a single strand like this, we could work out the details of the nanoflares, and that would teach us a tremendous amount. But as I've tried to emphasize, we're unable, at least now, to detect individual strands. Our spatial resolution is just not good enough. And even with high spatial resolution, there's still the problem of all the line of sight overlap, because the emission is optically thin in the corona. So we're always looking at overlapping strands. But what if we did have a really good spatial resolution? Would this overlapping really just kill everything so we wouldn't be able to do much? Well, that's indicated here. On the right, I'm going to show you a movie. This is a simulation. This field of view is very small. It's 1,000 kilometers on a side. So this is roughly an observational pixel from present day instruments. Within this pixel, there are 1,250 strands, a huge number of strands. So this observation is very deep along the line of sight direction, 50,000 kilometers. So it's quite realistic for a real coronal observation. And these strands have a diameter of 200 kilometers, which is what we infer based upon the observed properties of the kilogauss flux tubes in the photosphere. I'm going to heat these strands with nanoflares selected randomly from a distribution, a power law distribution. And many properties of this distribution are in fact quite realistic. The characteristic delay between events, the time average energy flux, those are all consistent with what we know from observations. All right, so I'm going to imagine looking at these many strands in the 94 angstrom line of iron 18, which has its peak contribution at about 8 million degrees. Here we go. All these nanoflares are going to go off. You're kidding me. Oh, there it is. Okay, phew. I couldn't see the bar. All right, so here the nanoflares are going off and all these 1,250 strands. Individual strands are brightening and fading. And the really great thing is, despite all the overlap, we're able to detect individual nanoflares and see individual strands. They do not get completely washed out. This is super exciting. It tells us that if we could achieve this kind of spatial resolution, we could observe individual nanoflares. Now, we're not there yet. Even the high-C rocket experiment, that image is reproduced on the left here, it has a resolution element that's about, a third or so of my simulation field of view. So high-C wouldn't detect these individual strands. It could maybe sense a hint of them, but you couldn't do any kind of detailed studies. But that situation may change in the near future. There's a technology called a photon sieve, which is essentially a Fresnel zone plate. There's a mission called VISORS, an NSF-funded mission, which is going to demonstrate this technology, hopefully successfully. The mission is going through CDR right now. Hopefully it will fly in 2 years. And this VISORS mission will have a resolution just a bit better than the high-C rocket. But Adrian Daw and the other technologists on the mission tell me that if it's successful, as they fully expect, it will be straightforward to have a quantum leap in resolution, to get resolutions an order of magnitude better than VISORS. So we would achieve the kind of resolution represented by this movie. So the future, I think, for understanding nanoflares is really, really exciting. All right, so all of these simulations I've shown you so far are hydrodynamic simulations. We have a rigid magnetic flux tube. We assume the properties of the heating, the properties of the nanoflares, and then we compute how the plasma responds and radiates. That's done very, very rigorously. But if we want to understand the energy release process itself, what causes the nanoflares, we have to use MHD. And a number of different groups around the world are studying coronal heating with MHD simulations. We are as well, and I want to briefly go over some of our results. This is work with Kalman Knizhnik and Vadim Uritsky. Also, Spiro Antiochos and Rick DeVore played very important roles in the original simulations that led up to this one here. I don't have time for details, but I'll simply tell you that we start out with a uniform magnetic field in plasma. We impose boundary flows meant to represent photospheric convection. So the field gets tangled and twisted, reconnection sets in, and eventually we reach a statistical steady state where the energy pumped into the field by the driver flows is balanced by the energy extracted from the field by the reconnection, which heats the plasma. So this on the right is a map of current density in the midplane of the simulation. It's a plane that cuts through the magnetic field lines. Very complex, many small current sheets in a sort of a web. Here is a map, corresponding map in the midplane of the emissivity as would be detected by the 193 angstrom channel of SDO. So the plasma here is at about 1.5 million degrees. I need to stress, this is not a coronal image. This is emissivity, which is a volumetric quantity. It's radiant energy per unit volume per unit time. An image is, of course, 2D. So to get the intensity in a pixel of an image, you have to integrate through the volume along the line of sight. What I'm showing here is emissivity in the midplane, cutting across the field lines. So here's a movie of that, I hope. There it goes. All right, so we're building up to the statistical steady state. There we go. So what do we see? Well, a couple of things really. There's kind of an overall, like a twinkling going on with nanoflares popping off here and there and everywhere, seemingly uncorrelated. In addition, there are places where there is a cluster of brightenings. Regions where, localized regions where many events are happening close together over a fairly short time window. Go through the movie again. There's going to be a cluster in kind of the upper left. There it is. You see other clusters like this. So two components to the emissivity, the twinkling of uncorrelated events and the clustering of events that have some kind of a collective behavior going on. Well, how do we relate that to observations? Well, images of the corona also have two components. There's a diffuse component and a bright loop component. Now, many people are under the wrong impression that the space between bright loops is very faint. That is not the case at all. In fact, the diffuse component of the corona is brighter than the loop component. So we suggest the following. We suggest that the diffuse corona comes from these uncorrelated nanoflares happening everywhere throughout the volume, whereas bright loops are from these clusters of nanoflares or nanoflare storms. And we're very encouraged by the agreement between this emissivity that we compute and coronal observations. For example, the diameters of these clusters are similar to the observed diameters or observed widths of coronal loops and images. The lifetimes of the clusters are similar to loop lifetimes. And also the shape of the clusters. These clusters represent the cross sections of loops. And this emission here, this kind of complicated emission, is contained within an envelope that's roughly circular. I mean, just roughly. It does not have a huge aspect ratio. And that's exactly what we've inferred from coronal observations. So we really feel that we're on the right track here. All right, what determines the properties of these nanoflares? Properties such as their magnitude, their duration, their frequency of occurrence, and also the collective effects that are responsible for these nanoflare storms. Well, there are three factors that dominate the answers to these questions. First of all, the onset conditions for reconnection. This determines the energy that's available for heating. We have the stressing going on from the photospheric driving, building up stress in the field, then the field breaks and releases the energy. But how much energy is available to be released depends upon how much stress we can build up. If reconnection happens too readily, if the onset conditions are mild, then we can't build up much stress, and therefore there's not much energy available to power the nanoflare. And this is true for any phenomenon that involves the slow buildup and sudden release of magnetic energy. It includes flares, coronal mass ejections, coronal jets, and magnetospheric substorms. Because the energy available to power a substorm depends on how much loading of the field can take place in the tail before the substorm begins. So the onset conditions for magnetic reconnection, this is a fundamental aspect of the reconnection process. And right now, Living with a Star focused science team devoted to the topic. You can hear talks later in the week on that if you're interested. Okay, another factor, the rate of reconnection. That determines how quickly energy is released. If the reconnection is very fast, you release the energy all of a sudden. If it's slow, of course, you spread out the energy release over a long time. And this affects things such as how high a temperature you can achieve in one of these nanoflare events. Third, the duration of the reconnection. Once reconnection switches on, for how long is it sustained? When does it switch off? This determines how much energy is ultimately released and how frequently the events occur. If a lot of energy is released, you've sucked out a lot of the stresses from the field, and it takes a long time to build back up to those critical conditions for the next release. Alternatively, if only a small amount of energy is released, the buildup time is very short. So this is the difference between low frequency and high frequency heating. All three of these, but especially the latter two, involve a coupling between small and large scales. Reconnection changes the conductivity of the magnetic field. That alters the large-scale magnetic stresses. The field responds to those changing stresses, and this feeds back on the reconnection. Very important coupling going on here. I'll say more about that in a moment, but let me first spend a little time on reconnection onset. To study onset numerically, it's vital to adequately resolve the current sheet, including its internal structure. And that's a real challenge if you're looking at systems with several current sheets. It's totally out of the question for an entire active region where you have 100,000 of the darn things. So our approach has been to look at individual current sheets and resolve them as well as we possibly can. This is work with James Leake and Lars Dahlgren. Sorry, Lars. It's hard to concentrate with all this noise coming from next door. All right, so we've looked at equilibrium current sheets with different properties, different lengths, thicknesses, and shear angle. Now the shear angle is the rotation of the field across the current sheet. If you have anti-parallel fields, then the shear angle is 180 degrees. But if there's a guide field component, the shear angle is smaller. And that's the case for the coronal heating problem. Remember, we have these misaligned strands, they're just mildly misaligned. So the shear angle is rather small. It's not 180 degrees like what you get when you have anti-parallel fields. All right, so on the top left here, this is a view of one of our current sheets looking down from above, kind of at an angle here. The magnetic field would be pointed, for example, to the right below the sheet, to the left above the sheet, and there's a guide field component into the board. And you see a lot of structure here. You see these inclined features. Well, reconnection begins with the tearing instability. And these inclined features here are associated with oblique tearing modes. These oblique tearing modes play a very, very important role. On the right, I also show current density. These are for end-on views of two current sheets. The one on the bottom there is a long current sheet with a small shear angle. It's evolving in a fairly organized way. There are a couple of plasmoids here. They're in the process of coalescing. Up above is a short sheet with large shear. The behavior is fundamentally different. We don't have nice plasmoids. We have a whole crazy mess. This is something some people might refer to as turbulent reconnection. So what we found from looking at these many different equilibrium current sheets is whether and how fast reconnection occurs. And by how I mean, do you have nice organized plasmoids or complex turbulence? But whether and how depend on the relative growth rates of the linear tearing modes. Again, the instability is a tearing instability that sets off the reconnection. So to me, this is really fascinating. It says that what is happening at the very earliest times when the disturbances have very, very small amplitude, that sets the stage for what will happen later as the system goes nonlinear. And that nonlinear behavior is very different depending upon the properties of the sheet. So we find that these properties depend on the relative growth rates of the tearing modes. And these relative growth rates in turn depend on the properties of the sheet, thickness, length, and shear angle. So if we know those properties of the sheet, we can predict how it will evolve. If you'd like to learn more, please go see James's talk on Wednesday, I believe. All right, so let's return to this the small scale, large scale coupling and how it affects the development of reconnection. And I want to emphasize an effect which I call patchy reconnection. I think it's really an underappreciated effect. And the consequences of that involving interlinking of field lines can be quite dramatic. So reconnection, it doesn't typically happen at one nice spot. It happens at multiple spots. We have clear evidence for that in observations. On the sun, we have observations of irregular flare ribbons. They're irregular both spatially and temporally. We have super arcade downflows in the flare arcade. In the magnetosphere, we have the completely analogous phenomena of irregular auroral ovals and bursty bulk flows that occur in the tail during substorms. Also in the magnetosphere, on the day side, we have flux transfer events. All of these are clear indications of patchy reconnection. And we see plenty of patchiness also in the simulations. So as a consequence of that patchiness, we can have interlinking of field lines. So let's see, I wish I had my pointer here, try to describe it. Okay, here I'm imagining in this cartoon current sheet, this light blue current sheet, there's reconnection happening in a patch sort of up in the top left. So we have reconnected field lines pulling away to the right. There are also reconnected field lines pulling away to the left that I don't show. Then there's a second patch of reconnection off to the right. And I show the field lines pulling away from that patch to the left. I don't show the ones pulling away to the right. But these two reconnections can happen and behave independently of each other. I mean, these field lines can easily slip past one another. These two reconnection sites do not influence each other. But now, what if we have a guide field? It's a much different story. Now the field lines pulling away to the right are linked up with the field lines pulling away to the left. And this will inhibit the reconnection because in order for reconnection to proceed efficiently, field lines have to get out of the way to allow new field lines to come into the reconnection site. This interlinking, basically it gums up the works. It'll slow down the reconnection and perhaps even quench the reconnection, shut it off altogether. Now we have observations of such interlinked field lines. Marit Oriaset and her colleagues looked at some MMS data of the magnetopause and found what they interpret as clear evidence of interlinked field lines. Now, these patches, they can be quite extended, and we have the possibility of two patches in which a single field line reconnects at both patches. That's shown at the top right. And we form, in this case, a flex rope. That's also true when there's a guide field. It's a twisted flex rope, but now note importantly that the ends of this flex rope are connected to the external field at the ends of the flex rope. So this connection here will prevent this flex rope from freely slipping through the plasma. And this will once again slow down the reconnection. All right, so we can have widely separated reconnection patches. Even within one single reconnection area, we can have local hotspots. And there's an interlinking of field lines associated with those local hotspots. That's the case with turbulent reconnection. And our simulations provide clear evidence that this slows down the rate of reconnection. Here are the results from 6 simulations. I show the inflow Mach number versus shear angle. And the inflow Mach number is based on the alpine speed using the reconnecting field component. And these values have been multiplied by 1,000. So 10 here is an alpine Mach number of 1%. In shear angles, I have shear angles of 20, 40, and 80 degrees, rather small. But once again, this is what's appropriate for the coronal heating problem. Now, for each shear angle, I have 2 simulations, both a 3D and a 2D version. They're identical with the exception that in the 2D version, everything is invariant in the guide field direction. So what do we see? For all of these shear angles, the rate of reconnection in 3D is much slower than 2D. This is expected based upon this interlinking business. Because in 2D, there is no interlinking. Interlinking is fundamentally a 3D effect. So it's precluded in 2D. So we have it in 3D, not in 2D, and the 3D is much slower. Also notice the difference between the 2D and 3D rates increases with shear angle. Again, consistent with our interpretation. Because at larger shear angles, we have more oblique modes in the system, oblique tearing modes. So more opportunities for reconnection, for patchiness, and for interlinking. So this business about patchiness, which is underappreciated in my view, and its consequences, I think is something that we really as a community need to think about a lot more. So let me, before summarizing, end with something very speculative. This is outside my realm of expertise. It may be that what I'm going to present to you is totally crazy. Please let me know if it is. But here goes. I'm going to suggest that there are many current sheets scattered throughout the magnetosphere, like there are in the corona. And these would be small angle current sheets. So guide field dominates over reconnecting field component. If they exist, they might explosively reconnect, giving rise to impulsive heating, maybe particle acceleration, and perhaps contributing in an important way to these ionospheric upflows. So why do I think that's the case? Why might they exist? Well, here's my cartoon of the magnetosphere as viewed from the side. The sun is to the left. I show 2 field lines about to reconnect, red and blue. So they map down to the edge of the auroral oval. This is during a substorm. So the field lines reconnect, producing a purple field line. It retracts toward the Earth, and the field dipolarizes. And now I've allowed the auroral ovals to migrate toward the poles because some time has elapsed, and that's what we have during substorms. Now, in this case here, there is no BY component to the field, no component into the board. So these field lines are contained within the midnight plane. Let's suppose we do have a BY component. So here's a different view. This is looking at the magnetosphere from above the North Pole. There's a BY component. I'm imagining that the solar wind has a BY component, an east-west component. It reconnects with the magnetosphere on the day side, and the lobe field lines, which are formed, which drape back into the tail, those still have that BY component. So the configuration will look as shown here. Again, this is a view from above. So I have 2 red field lines just above the current sheet, 2 blue field lines just below. Now, if these field lines reconnect, if the dark red and dark blue field line reconnect, they'll do so out to the right, farther away from the Earth, forming a dark purple field line, as shown on the bottom. And this field line has shear. The foot points are separated in longitude because of this finite BY component. Now, if the light red and light blue field lines reconnect, they'll do so closer to the Earth, forming the light purple field line. Also sheared, but not as much. the separation of the foot points and longitude is not as great. Now, these field lines pass right by each other at midnight. They're basically part of the same L shell. So there's a steep gradient in BY at that location. In other words, a current sheet. So if reconnection is happening in a patchy way in the tail during a substorm, happening at various locations from the Earth, will form many such sheared field lines with different amounts of shear. So there will be current sheets embedded within that reconnecting field. Places where in principle, we can have impulsive energy release. Now, maybe crazy. No one is fidgeting too much in their seat. I've run this idea past some of my geospace colleagues, and they haven't noticed anything that causes them to just reject this outright. So I think it's worth thinking about. And I would note that I've estimated the amount of free energy in this sheared field, and it is not insignificant compared to the thermal energy in the magnetospheric plasma. So potentially very important energetically. All right, time to summarize. First of all, active regions are heated primarily by nanoflares. The properties of nanoflares, especially their frequency, determine the thermal distribution of the plasma and therefore the spectrum of emitted radiation. As I pointed out, this has important space weather consequences. In this context, I'd like to announce a new group in the International Space Weather Action Team. It's a group that Sam Schoenfeld and I are putting together, trying to understand solar origins of the solar spectral irradiance and its intermediate timescale variability. It's not variability associated with big flares, but variability associated with the evolution of active regions and the rotation of active regions onto and off of the disk. And the consequences of that are very important. Present day models of the solar spectral irradiance are empirical or semi-empirical. We'd like to look at physics-based models of the solar spectral irradiance. So if you're interested in joining our team, we'd be delighted to have you. Please contact either me or Sam. All right, this problem involves an enormous range of spatial scales, at least 6 orders of magnitude. And there is very important coupling between scales and between different parts of the atmosphere. It's these two aspects, the extreme range of scales and the coupling, that make the coronal heating problem so incredibly difficult. I mean, it would be great if we could perform one massive do-it-all simulation that gets everything right. No way. I mean, we're not even close to that. So we're forced to concentrate on specific aspects of the problem, kind of in isolation. But it's dangerous to work in total isolation because all these different aspects impact one another. So it's important as a community that as we work on our little part of the problem, we pay very close attention to what other people are doing on other parts. And what they're doing can maybe feed into what we're doing and vice versa. We have to communicate better. Okay, I've pointed out some commonalities with geospace. There's the analogy of ionospheric upflows and chromospheric evaporation. I've emphasized the importance of the onset of magnetic reconnection for all these explosive phenomena that occur throughout the universe, not just on the sun, not just in the heliosphere. I've talked about the patchiness of reconnection and how that results in the tangling of field lines, which can impact the way the reconnection develops and the reconnection rate. I suggested that maybe there are current sheets scattered throughout the magnetosphere, like in the corona, and therefore the possibility of magnetospheric nanoflares. So my last slide, in fact, here is, can't see the buttons, is an advertisement for the Triennial Earth-Sun Summit, or TESS, which will be taking place this summer in August. It's going to be in Bellevue, Washington, basically the outskirts of Seattle. As I hope you know, the point of TESS is to bring together the different sub-communities of heliophysics to get us to interact more. And so the TESS meeting will have discipline-specific sessions, but we really want to encourage cross-disciplinary sessions. There's going to be a call for proposals, session proposals, imminently, and those proposals will probably be due at the end of January. So I encourage you to take advantage of this opportunity here at AGU, talk to your colleagues, come up with some ideas for nice sessions for the TESS meeting, and help us to make this the most successful meeting we possibly can. So with that, I thank you very much for your attention, and I welcome your questions and your comments and your criticisms. Thanks.
That's not going to go on. Thank you very much, Jim. We do have a number of questions here, some online. Let's see. few hundred.
So I wonder, why didn't they close that wall completely? Why did they leave that opening?
Yeah, hopefully people in the back can't hear the other room as badly as we do.
That's
And I have to apologize, I was in the wrong time zone when you started. And also apologize to people online because it took almost a half an hour to get your slides up. But there are a number of questions online, and then we'll take a couple of questions online and then a couple of questions from the audience. So the most popular questions are you able to connect these models to surface magnetic field observations? And can you produce a data assimilation model?
People are working on that. People much smarter than I. That's a very important thrust, exactly that. I mean, there are these incredible models by people like Matthias Rempel, where they don't suppose some kind of surface flows. They actually, in their model, they have a convection zone, and they compute convection, and they have the field sticking out in the corona and the coronal response. Really impressive models. But I would point out, we take these different approaches, and every approach has its strengths and its weaknesses. And that approach, as amazing as it is, it doesn't capture all the many, many current sheets that we're quite convinced exist in the corona. And I would argue it doesn't capture properly the way those current sheets reconnect. It's more sort of ohmic heating of distributed currents rather than explosive heating in this enormous number of very thin current sheets.
Thank you. Maybe we'll take a question from the audience now. Yes?
Mhm.
And if you
Yeah.
could,
Yeah.
if you could summarize the question
Yes.
briefly for the
Okay.
people online.
So Dana asked about the role of enthalpy and whether that sets important enthalpy associated with evaporation and whether that sets important time or length scales in the corona. It does, in the sense that unless you adequately resolve the transition region in your models and get that thermal conduction right, you're not going to properly model the evaporation. And therefore, the density and temperature of your corona are going to be wrong, and any kind of predictions you make of observations are going to be off, sometimes way off. So in that sense, there's the time scale of the evaporation process. Length scales, only in the sense that if you have two adjacent strands, one's evaporating, one's not, you can have a big difference in density and temperature from strand to strand, so that's a length scale. I'm not sure if that's what you were after, sorry.
Thanks. Yeah, unfortunately, we have run out of time. We need to have a couple of minutes to change over speakers. But Jimmy, you can actually get into the chat on Zoom and answer some of the questions there or on the app, or for people in the audience, please grab Jim in the hallway. And thank you for a fabulous talk.
Thanks, Jeff. Thanks very much. Thanks, everybody.